Welcome everyone to this 8th lecture of states of matter. So in the previous classes, we have seen about the kinetic theory of gas. We have also seen its postulates and the explanation for the postulates. Further, we have also derived the expression that kinetic energy of molecules is directly proportional to temperature and it's directly proportional to the square root of velocity. Further, we have also seen the explanation of the gas laws on the basis of kinetic molecular theory of gases. That is, we have seen the molecular origins of Boyle's law, Charles law, and Dalton's. Also, in the previous class, we have touched upon the Maxwell-Boltzmann distribution. So, in this class, what we are going to do is we are going to dive deeper into this Maxwell-Boltzmann law. Further, we are also going to understand what is Maxwell's distribution, and then we are going to study about different kinds of velocity which exist, and then we'll go solve some example. Let's create states of matter. The first topic which we are going to cover today is Maxwell-Boltzmann distribution. Maxwell-Boltzmann distribution of molecular speeds. As gas consists of tiny particles spread from one another by very large empty spaces, these particles are constantly moving in all directions. During their motion, they collide with one another and also with the walls of the container. As a result of this collision, the speed and direction of the molecules go on changing, and thus all the molecules present in the given sample of gas do not possess the same speed, right? What we have is all the molecules in the gas do not possess same speed. The speeds of individual molecules are different and and are distributed over a wide range. Even if all the particles had the same speed initially, due to the molecular collisions, they will have different final speed, right? And hence the speeds of the different molecule go also on changing. However, the distribution of speed among different molecules remains the same at a particular temperature, although the individual speeds of the molecules may change, right? This is also an important point which is however, even though the speeds of individual molecules may vary, the distribution, however, the however, distribution distribution of speeds among different molecules remains remains the same at a particular temperature. Thus, the fraction of the molecules with a particular speed remains constant, and this is what is known as Maxwell-Boltzmann distribution. The third point is, thus the fraction of molecules with a particular speed remains constant. Maxwell-Boltzmann distribution, well, Boltzmann distribution law, because they were first to formulate it, right? First to formulate it. So what they did is basically they plotted Maxwell and Boltzmann plotted the fraction of the molecules, plotted the fraction of molecules, which is nothing but delta n by n, or you can also write it like this, along y having different speed against the speed of the molecule, against the speeds of the molecule. This is going to be on x axis, right? And the curve so obtained is like this. The curve which is obtained is like this. Like this. This is the origin, right? The curve which they obtained. This is the nature of the curve which they obtained. This is going to be what? This is the x-axis. X-axis denotes molecular speeds. Molecular speeds is going to be centimeter per second, right? And this is going to be delta n by n. This is the fraction of molecules having a particular speed, and this speed, this right here, the peak of the curve is what we are calling it as the most probable. Probable is denoted by UMT. So, as per this law, what we have is the important features of the important Maxwell's, the fraction of molecules with low or very fraction of molecules with very low or very high speed is very small, right? Then the next is the fraction of molecules possessing higher and higher speed goes on increasing till it reaches the peak, and then it starts decreasing, right? Fraction of molecules possessing higher speeds goes on increasing till it reaches, and then it starts decreasing. The third point is going to be the maximum fraction of molecules possesses a speed corresponding to the peak in the curve. The curve corresponding to the peak is called as the most probable speed, right? The maximum fraction of fraction molecules possess possesses a speed possesses a speed corresponding to the peak of the curve, right? Corresponding to the peak of the curve, to the peak of the curve, right? And this is what is called as the most probable speed, right? The speed corresponding to the peak, the speed corresponding to the peak, to the peak is called as most probable speed, most probable speed, which is UMP. Thus, the most probable speed of the gas is the speed possessed by a maximum fraction of the gas molecules at a given temperature. Right? What is most probable speed? The most probable speed of a gas, most probable speed of a gas is the speed possessed by the maximum fraction of the gas molecule, the maximum fraction of gas molecules at a given temperature. And it is generally denoted by UMP. It may be noted that as long as the temperature of the gas is constant, the fraction having the speed equal to the most probable speed remains the same. But the molecules having their speeds may not be the same, right? In fact, the molecules keep on changing their speed as a result of collision, right? So this is very important. I'm going to write. So it may be noted that as long as the temperature of gas is constant, of a gas is constant, the fraction having the fraction having the speed equal to the most probable speed equal to the most probable speed remains constant or remains the same, right? But the molecules having this speed may not be same. Having this speed may not be same. Right? In fact, the molecules keep on changing their speed. The molecules keep on changing their speed as a result of collision. It may be noted that the speed distribution at a particular temperature also depends on the mass of the molecule. It may be noted that the speed distribution at a particular temperature also depends upon the mass of the also depends upon the mass of the molecules. At the same temperature, gas molecules with heavier masses have slower speed than lighter gas molecules, right? At the same temperature, at the same temperature, gas molecules having with heavier masses, gas molecules with heavier mass have slower speed than lighter gas molecule, right? Then lighter gas molecule, right? For example, let me draw a figure, y-axis, and this is x-axis. This is origin. Here we have molecular speed, right? And here we have fraction of molecule. This is delta n by n, right? The first plot is like this. Let me draw it on a new page. So what we have in here is our y-axis, this is our x-axis, this is origin, and then we have a plot like this, another plot. So this plot is going to be chlorine, and this is going to be a nitrogen. So the atomic mass of nitrogen is 14, while that of fluorine is, or should I say that molecular weight of fluorine is greater than molecular weight of hydrogen, right? Most probable speed for fluorine, and this is going to be the most probable speed for UMP of Cl2, and this is going to be UMP of. From this figure, we can see that the lighter nitrogen molecules, right? This is the nitrogen curve for nitrogen. The lighter nitrogen molecules move faster than the heavier chlorine molecules. Therefore, nitrogen molecules have higher value of most probable speed than chlorine molecules at any given temperature, right? So this is going to be the speed, molecular speed, right? And this is going to be the fraction of molecules having a particular speed, right? So if you check at any particular fraction of molecule for nitrogen, so nitrogen is always going to have higher speed than the heavier chlorine, right? The next subtopic which we are going to study is effect of temperature. Effect of temperature. Temperature on the distribution of speed. On the distribution of speeds. So as already discussed, the increase in temperature of the gas results in increase in the molecular motion. Consequently, the value of most variable speed increases with increasing temperature. In fact, in fact, the entire distribution curve shifts towards right as the temperature rises. In other words, the curve broadens at a higher temperature, right? So the plot for this would be like this. So what we have in here is it's going to be my y-axis, this is going to be my x-axis, this is going to be the origin, and this is the fraction of the molecules delta n by n, and this is molecular speed. Molecular, so this is going to be like this, and then the second plot is going to be like this. So what we have in here, is this is the most probable speed, right? But at this temperature, and this is going to be the most probable speed at this point here. So this is going to be so the black plot is at temperature T1, and the purple plot is at temperature T2. This is going to be UMP at T2, and this is going to be UMP at T1, right? And T2 is going to be right, so T1, and this is going to be T2, and T2 is going to be greater than T2. Right? This whole plot we can say as distribution of speeds at two different temperatures. From this plot, what we can see is that as temperature increases, UMP increases. Why? Because this is greater than this one, right? UMP2 greater than UMP1, right? So this is the first point. The second point, as T increases, the entire curve shifts towards right. Okay. So apart from the most probable speed, which we have discussed, there are two other terms which we commonly use for gaseous molecules. Okay. So these are the speeds. There are three types of speeds which we have, right? So the first one is the most probable speed, which we have seen. Most probable speed, which we denote as UMP. The second one is the average speed, right? Which is denoted by UAV. And the third one is the root mean square speed. Root mean square speed, right? It is noted as URMS. Let us understand first the most probable speed. Most probable speed, it is UMP. It is number one. So it is the speed possessed by maximum fraction of the molecules of a gas at a particular temperature. It is the speed possessed by maximum fraction of molecule of a gas at a particular temperature. A particular temperature. Okay. Second one is the average speed. Average speed. It is denoted by UAV. So it is the average of the different speeds. Average of the different speeds of all the molecules present in a given sample of gas. Present in a given sample of gas. For example, if n is the number of molecules in a given sample of gas, in a given sample of gas, right? And let's say u1, u2, u3 up to ui are the speeds of individual molecule I. Then what we have is, then u average is going to be u1 plus u2 plus u3 up to un divided by total number of molecules is going to be n. The next speed which we have is root mean square speed. Root mean square speed. So this is the next speed which we have is this one. What is this? It is the square of, it is the square, it is the square root mean, square root mean, square root mean of the squares of different speeds of the molecules of gas, right? And it is represented by, it is denoted by URMS, right? So similarly, if ui are the speeds of individual molecules and if there are n molecules, then what we can say is URMS is nothing but u1 square plus u2 square plus u3 square plus up to un square divided by total number of molecules and the square root of this. This is what is the root mean square speed, right? Similarly, alternatively, what we can say is, alternatively, if u1 is the speed of n1 molecules, u2 is the speed of n2 molecules, similarly, un is the speed of n molecules, then what we have is, in that case, URMS is going to be square root of n1 u1 square plus n2 u2 square plus up to nn un square divided by n, or divided by n1 plus n2 plus n3 plus up to nn, right? And if you plot it on the plot, what we get is, we get a plot like this. This is the origin. This is molecular speed, right? And this is the fraction of the molecule. Right? This is the speed which we have. So in that case, we are going to have three different lines. So one is going to be this one. This is what is the. And the other is going to be this one. For example, take this one, this one, and the third one is going to be this one. Is slightly lower than that, right? So this is going to be URMS. The orange one is going to be U average, and the red one is going to be U most probable, right? And the caption is going to be different types of speeds in Maxwell Boltzmann distribution of speeds curve, right? Further, we also see that from this plot we see that U most probable is going to be greater than U average, which is going to be root RMS, and URMS is the directly proportional to this average kinetic energy, right? We also see some other aspects, which is the most probable speed for an ideal gas comes out to be this one, 2 RT by M, right? This is number one. Number two is going to be the average speed is going to be equal to 8 RT by M, and the third one, which is URMS is going to be equal to 3 RT by M, right? So when we take the ratio, what we get is UMP is to U average is to URMS is going to be is to 1 is to 1.128 is to 1.224, right? Similarly, what we have is URMS is going to be 3 RT by M, which is going to be equal to, for an ideal gas, RT is nothing but PV, and this is going to be nothing but 3P by rho, right? These are the various expressions which we should remember, right? Then let us move on to the solid example. So question 1, to calculate the kinetic energy of 2 gram of oxygen at minus 23 degrees centigrade, right? We know that is directly proportional to the root RMS, square root of this, right? Hence what we have is, sorry, what we have is EK is nothing but 3 by 2 nRT here, and is nothing but 2 by 32, which is 1 by 16, and R is going to be 8.314 joules per Kelvin mole, and temperature is going to be minus 23 degrees centigrade, which is nothing but 250 Kelvin, right? Therefore, EK is going to be what? 3 by 2 multiplied by 1 by 16 multiplied by 8.314 multiplied by 250. Therefore, kinetic energy is going to be 194.86 joules. Let's move on to the next question. This is question 2. Calculate the root mean square speed of root mean square speed of methane molecule at 27 degrees centigrade, right? Is going to be, the solution is going to be straight. It's going to be straightforward formula. URMS is nothing but root 3 RT by M. So for this thing, temperature is nothing but 27 degrees centigrade, which is 300 Kelvin. Mass of methane is molar mass of methane is 16 gram, and R is going to be 8.314, right? Therefore, URMS is going to be 3 into 8.314 multiplied by 300 divided by molar mass, which is going to be 16, right? Which is nothing but 683.9 into 10 raised to power 2 centimeter per second. Therefore, URMS is going to be 683.9 meter per second. This is very important. Moving on to the next topic, which is the behavior of real gases. Behavior of real gases and deviation from ideality. Deviation from ideal gas behavior. Okay. So gas which obeys PV is equal to nRT is called as ideal gas. So an ideal gas is nothing but obeys PV is equal to nRT, right? However, none of the gas there can exist a gas. In fact, there are many gases which do not follow this expression. Either the left hand side is greater than right hand side, or the vice versa. Hence, at best, the gas shows ideal behavior at low pressure and high temperature, right? Many gases show deviation to deviation from ideality, right? At best, what we have is gases show ideal behavior at low pressure and high temperature. At low pressure and high temperature. Right? As the pressure becomes higher and the temperature becomes lower, more and more deviations are observed from general gas equation. Right? As temperature decreases and pressure increases, deviation from ideality increases. Deviation from ideality increases, right? So gas which does not obey general gas equation and other gas laws at particular temperature and pressure is called as a non-ideal or real gas, right? So gas which does not obey does not obey general gas equation, general gas equation and other gas laws and other gas laws at all temperatures and pressure, at all temperature and pressure is called as a real or non-ideal gas. All gases which are actually known to exist, such as oxygen, nitrogen, carbon dioxide, etc., are real gases and they show ideal behavior to different extents. Most of these show ideal behavior at low pressure and high temperature. Right? Scientists have made extensive study of the behavior of various gases under different conditions of temperature and pressure. They concluded that the real gases do not obey the general gas equation under all conditions of temperature and pressure. To the best behavior of real gases, right? So a plot is plotted. So let us draw a plot. So this is going to be the y-axis. This is origin and this is x-axis. So here what we have is we have pressure. Here what we have is PV. So if the gas would have been ideal, what we have ideal gas PV is equals to nRT, right? So it should get a PV versus P plot should be PV versus P for ideal gas will be a straight line. For ideal gas should be a straight line, right? Straight line, right? Let's say is the straight line behavior which we obtain here. Right? So this is an ideal gas, right? Ideal gas. However, most of the real gases which we see is, let's say, this is number one. They follow behavior like this, right? This is gas one, and this is going to be gas two. It's going to be like this, right? Some gases don't even follow this. They are just a straight line, hmm, like this or like this, right? So what we have is this graph is for CH4, right? Then this one is for CO, right? And this is for H2, right? This is H2 and this is helium, right? This is going to be helium, right? So the best behavior of real gases, right? We have plotted PV versus P plot of gases at constant temperature, and according to Boyle's law, PV will become constant and V values versus P plots, all pressure will be a straight line parallel to x-axis, right? However, these are the real plots. So it can be seen from this figure that at constant temperature, PV versus P plot for real gases is not a straight line. There are significant deviations from ideal behavior, right? And two types of behavior are observed, right? Two types of behavior, two types of behavior are obtained from above graph, from above graph, right? Which is some gases, for some gases, what we have is for some gases, for some gases, for some gases, as the pressure increases, the value of P into V also increases, right? And for other gases, first there is a negative deviation, there is a negative deviation, negative deviation from ideal behavior, that means as PV, that means PV decreases pressure, right? It reaches to a minimum value. After that, PV increases with increase in pressure, right? Thus, real gases do not follow ideal gas equation perfectly at all conditions, and deviations from ideal gas behavior also becomes clear when the pressure versus volume plots are drawn. The pressure versus volume plot of experimental data and the theoretical data calculated from Boyle's law should coincide if all the gases behave ideally, right? So for this, let us plot this. When we do this exercise, the plot which are obtained as like this. So here we have volume and here we have pressure, right? So this is the plot for the ideal gas, okay? However, for real gas, the plot which we obtain is like this. It is more than that, and then it crosses the ideal gas and it becomes like this. Real gas, and this is going to be ideal gas. Plot of P versus V for ideal and real gases. So it is clear from this figure that these two do not coincide, right? At high pressure, the measured volume is more than that of the calculated volume, right? The measured volume is more than the calculated volume. However, at low pressure, measured and calculated volume almost approach each other. Measured and calculated volume almost approach each other. Approach each other. Okay. Let's say, for example, it should be like this. It should be like this. Okay. So in this class, what we have seen is we have seen the different. We have seen in detail about the Boltzmann distribution law. Then we have also further seen the various types of speed which exist. We have also seen the relationship of most probable speed with temperature and the mass of the molecule. Then we have established three types of different speed, which are most probable speed, average speed, and root mean square speed. Then we have seen the relationship between them. and the expression which is used to calculate them. Then we have solved some examples, and then we have delved into behavior of real gases, that is the deviations of real gases from ideality. We have seen that PV versus P plot reveal a peculiar relationship for ideal gas and for real gases. We have also seen the pressure versus volume relationship for real gases and ideal gases, and we have concluded that at high pressure the measured volume is more than the calculated volume, whereas at low pressure measured and calculated volume almost approach each other. Right? So in the next class, what we are going to study is we are going to quantify how this ideal behavior, a deviation from ideal behavior, can be quantified. Then we are also going to see the effect of temperature. Okay, and we are going to then at the end we are going to study about the faulty assumptions of kinetic theory of gases, which led to the development of new equation which considers the equation which is called as an equation for real gases and also known as van der Waals equation. Okay, so I hope you have enjoyed in this class and learned, and thank you for attending this class, and I hope to see you again in the next class. Okay, thank you.